So more examples. Express each of the following sets using the roster method. Set A is a set of natural numbers less than 5. And here we see that set. Remember, it's less than 5, so it cannot be equal to. So hence we see 1, 2, 3, 4 only. And the next two examples give you something similar. The last has interesting notation. So here we see the element symbol as well. So the set of all x such that x is an element of the natural numbers and x is even. So what values are natural numbers and even? Well, we can begin with 2, 4, 6, 8, and then we show the ellipsis to say that this continues in that fashion infinitely. This slide is giving us the same descriptions here in different ways. So we can either use inequalities, set builder notation, or roster method to define our sets. So the set builder notation and roster method is showing the example and giving you a description of the differences between strictly less than or greater than and less than or equal to, greater than or equal to. These are compound inequalities. So in the compound inequalities, I like to use the language between. So in the first compound inequality, we see that x is between a and b, where x cannot be equal to a and b because there is no equal to sign here. And here's that example. X is between 4 and 8. So we have 5, 6, 7 to represent the natural numbers that are between 4 and 8. But in this example, we have the or equal to symbol, and hence we see 4 and 8 as our endpoints. So express each of the following sets using the roster method. So the first set is the set of all x such that x is an element of the natural numbers and x is less than or equal to 100. Notice we always start from least to greatest, even though if we included all of the elements in this set out of order, it would still be a set. It's just easier to list them this way, especially since it's a larger set. We can do the same with B. Cardinality is speaking to the number of items in a set. So if I have the set of all bicycles that I own, I would count them to find the cardinality. So if I have 10 bikes, the cardinality for my set of bikes that I own would be 10. And we use the notation n of A, or the number of elements in A. So here are examples of these. I'm sure this is a pretty simple concept, so I will continue. Now here is an example of a definition of a term that may sound familiar or similar to another. So be very careful with this term and the next to distinguish between the two. So equivalent sets do not mean that they are equal. Equivalence only means that their cardinality is the same. So the number of elements in one set is the same as the number of elements in another set, and therefore they are equivalent. Here's an example. So I have two different sets, the set of all x such that x is a vowel, and then B, the set of all x such that x is a natural number and x is between 3 and 7. Well, obviously, listing out those elements, each set has 5 elements. And because each set has 5 elements, the two are equivalent. Here's another example. A real-world example of preferred age difference in a mate. This one is kind of funny. So we say A is the set of 5 countries shown, and B is the set of the average number of years women in each of these countries prefer men who are older than themselves. Are these sets equivalent? So looking at the information there, we see that in each set, there is the same amount of information, or so it seems. So A is the countries. So we have Zambia, Colombia, Poland, Italy, and the US. And B has a value that corresponds to each of those countries. However, one of the values corresponds to 2 of the countries. Since the value is the same for each, we won't list it twice. Hence, there's only one value there that is unique, 3.3. And so we only count it once. So there are only 4 values in the second set, but 5 in the first. So are these 2 sets equivalent? No, they are not. Each value in the set only is counted once, each unique value. If there are multiple of the same, we do not recognize it as a different element. Finite and infinite sets. So a finite set, if n of A, meaning the cardinality of A is 0, or n of A is a natural number. So this is the way that we can distinguish a finite set from an infinite set. So can we count the number of elements in the set? Or does it continue on and we're not able to number those elements? So if we're not able to number the elements, it's infinite. Like the natural numbers, it continues on forever. So we're not able to count those values. Now we get to equal sets. So unlike equivalent sets, equal sets must have the exact same elements. And these elements, of course, also must be counted and the same. So here are some examples. The first, A, those 2 sets are definitely equal. They have the same number of elements and the same elements themselves. Even though they're in a different order, they're the same elements and hence equal. In B, there is an extra element. 0 is not a part of the first set. Hence, they are not equal. So this concludes the first slideshow and presentation. I hope it was helpful. I'm sure the next one will be better. I just need to figure out the setup here. Go ahead and go through the other slides, and I will post another video, but definitely leave me comments on questions that you may have from this section and from the homework as well. I'll talk to you soon.